Hello class, and welcome to our next day of scientific notation / exponents, and we're actually getting back to scientific notation. We did one day of it to begin with, but it was just converting between standard and scientific notation. And then we took a little break and did some exponent work. But we're back to scientific notation. We're actually multiplying and dividing numbers that are written in scientific notation today. Next class will be adding and subtracting, and that'll complete some of the tougher things we have to do with this unit. Especially tough because you cannot use a calculator for this. We're going to jump right into an example, but I also am going to take some time to explain why the rules that we use work. So I think explaining it will help you understand and maybe help you remember it a little bit easier. Alright, so this is a typical problem you might see. We'll start it with, it's really big there, 3.5 times 10 to the third. And we multiply that by 2 times 10 to the fifth. Okay, so notice both are written in scientific notation. They would be pretty easy to convert if I wanted to, but we're not really going to do that. I'm going to actually kind of convert them just to show you why it all works, but after that we won't convert them at all, and it is actually much more work to try to convert them first. Okay, so the rule is really simple, and the rule is just like when we multiplied monomials. You take your coefficients. In this case, the coefficients are the first numbers. So 3.5 and 2, and you multiply them. So I'll write the rules over here. You're going to multiply coefficients. And what you get is 7. 3.5 times 2 is 7. And then you just do your times 10 to the, because every number written in scientific notation is like that. And then you add your exponents. Sounds familiar, right? It's exactly what we did in an example that might be like 3x squared times 4x to the fifth. We would say 12x to the 7th. Same exact rules. So in this case, it's 3 and 5. We get 8. And that's it. That's really how easy some of the problems are. But they get a little different when the number you get right here is too big or too small. So we'll have an example of that in just a minute. But the first thing I want to do is just show you why this all works. Okay, so off to the side, I'm going to write both of these numbers in standard form. So 3.5 times 10 to the third is the same as saying 5, and move the decimal over 1, 2, 3 times, so it's 3,500. And then we're multiplying that with 2 times 10 to the fifth. That's just 2, move the decimal over 5 times, you end up adding 5 zeros. Okay, so it's 3,500 times 200,000 really is what we have. Alright, and if we remember from our multiplying big numbers back in the day rule, if it ends in 0, we can just kind of ignore them for a little while. So we're going to take these zeros, ignore them, just do 35 times 2, which is 70, and then add the zeros back on. So in total I have 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7. If I wanted to write this in scientific notation, that would be 7 times 10 to the 8th, because it's from here to here, there's 8 spaces. So there's one way. But even better, if I don't change the structure, if I just say 3.5 times, I'm going to use a dot this time, times 10 to the third. 10 to the third is just 10 times 10 times 10. And every time you do that, you add another 0. So it's 1,000 times 2 times 10 to the 5th is that 100,000? I think so. 1, 2, 3, 4, 5. Yeah, 100,000. And since every single operation here is multiplying, and multiplying is commutative, so commutative means that you can do it in whatever order you want, it will turn out the same, just like 5 plus 2 is the same as 2 plus 5. So I can rearrange this so that it's 3.5 times 2 times 1,000 times 100,000. Now, do you see what I have here? I have 3.5 times 2 part, which is what I did in the very beginning, and that's 7. And then I have the 1,000 times 100,000, or in other words, 10 to the 3rd times 10 to the 5th part, which is exactly what I multiplied to get 10 to the 8th, because we know if we have the same base, we keep the base and add exponents. So that's where we get our rule from, because it works every time. You certainly don't have to show all this work to the right every time or any times, as long as you understand what's happening. As long as you remember the rule that I erased already, that you multiply coefficients, add exponents. Alright, let's try a new example. Alright, so here it is, and we're going to start by multiplying coefficients. And I know that seems pretty ugly, especially when I remind you that you cannot use a calculator. So if this was a test or classwork, this is something you're going to have to do off to the side. Remember, you just ignore, when you're multiplying, you don't have to line up any decimals or anything. You just multiply like normal. You get 5. 5 times 4 is 20. Bring down an extra 0 when you go to the next line. 3 and 12. Alright, so I'm not going into too much detail here on how to multiply. If you're stuck on that part, we can work on it. Remember now, this is where the decimal comes in. There's 2 digits after decimals in total, so I make sure there's 2 digits after a decimal down here, and you get 14.35. Alright, then times, this is the easier part, just add up -3 and 7. And it's really like saying 7 minus 3, which is +4. And we're not done. I don't know if you can tell why we're not done. This number right here is too big. We only want 1 digit before this decimal. So what we have to do is remember our rule for what happens when we move decimals. So really, what I really want is 1.435 times 10 to the something. But I can't just keep it 4, because that told me something about the decimal, and I just moved the decimal, so it shouldn't be telling me the same thing. Remember the rule was, let's see if I can draw really well again. Oh, this is way worse. So you hold up your hand, and hopefully your hand looks a little different than that, and you make an L for left, which is the direction that we moved our decimal in, and your finger points to the direction of the exponent. So when you move the decimal left, the exponent goes up. So it's now 1.435 times 10 to the 5th. So once in a while when you multiply, you have that little extra step. Alright, we're going to switch over to division now, and if you remember how closely matched the multiplication rules for scientific notation were to monomials, the same thing's going to happen with division. So if I remember right, with coefficients, you divide them. So we're going to say divide coefficients. And then for exponents, can you remember what you do? You subtract them. So subtract exponents. There was one thing we always said was keep the base, keep the base. That is still true too. The base in every single scientific notation problem is a 10. And we always keep the 10. So that part's the same too. Alright, so off to the side, you're going to do this little division of 8 divided by 2.5. So I like to write the old classic long division way. And I don't like having a decimal here, so I move it over. And I move this decimal over. And you bring it up. So everything's set up. So I'm really kind of doing 25 into 80 now. Well, I know if it's, I think quarters when I see 25, so 3 of them would be 75. Subtract, you get 5. 25 can't go into 5, so we bring down some extra decimal, or excuse me, extra zeros after the decimal. 25 can go into 50 exactly 2 times, and that'll be the end of it. So we get 0. So 3.2 times 10 to the, and again, this is the easier part, subtract exponents. 6 minus 3 is 3. And look at that. It does not need to be fixed. 3.2 is a number between 1 and 10, and we're good. Alright, here's the last example we're going to do together. And this time, when I'm dividing, the number 8 that's going into 2.4 is bigger. So just keep in mind that's certainly possible. Don't just switch it because it works better the other way. It actually works very well this weird way. So off to the side, I'm going to try to figure out how many times 8 can go into 2.4. I don't have to move a decimal around or anything like that. I just bring it up, pretend I'm just doing 8 into 24, and I only have to do it. I don't do anything special. 8 goes into 24 3 times. It's just that the decimal is right here. So it's 0.3 times 10 to the, and then this is the other tricky part. I'm subtracting here. So in my head, I'm thinking -4 minus 6. So if you write it out, you're going to not make a mistake. If you're just trying to do this in your head, you may do it in the wrong order, you may put an extra negative in, but write it out. Here's the first one, here's the second one, and here's me subtracting it. So -4, take away 6, that gets you -10. So it's times 10 to the -10. Okay, now we have a problem though, because I don't have any digit before the decimal, and I need one. So I'm going to have to move this to the right, and I get 3 times 10 to the, okay, and here's where the hand rule comes in. So let's see if I can draw my amazing hand here. Here's my thumb, here's my finger pointing down, here's your other fingers. There we go. So it makes a little R. When you move the decimal to the right, like we did, the exponent goes down. Down from -10. So think about a number line, right? You have 0 in the middle, maybe 10 over here, we have -10 over here. Down is that way. And that puts us at -11. Just be careful what up, down means when you're in the negative world. And that's it. That's our answer. We followed the rules and we fixed it at the end. Alright, we're going to end this video with something you're going to try on your own. So this is multiplying. You can go back and watch those other 2 examples once if you want. And please resist using a calculator. If you must only use it to check, please try it without first, because that is how it's really going to be. Alright, good luck, and I'll be checking this problem when you come in. Good night.